Hey, welcome back to set builder notation and interval notation. In this first video, we're going to talk about set builder notation. This is one of those cool videos where it looks really difficult at first, and when I first show it to you, you're going to freak out, but you're going to get it really soon, and then you'll be able to do it to your little brother and sister, and they'll be like, what are you doing, writing in some foreign language? So let's talk about it. So today, by the end of this video, you should be able to write the solution to an inequality, to inequalities in set builder notation. And so what is set builder notation? It is a shorthand way to write a solution set, answer to an equation. You're like, well, Mr. Craig, Mr. Nelson, Ms. Garcia, I already know how to do that. You're right. If I gave you an equation like this, we already know that x is my variable, this must be my constant, and so I'm gonna get rid of that by subtracting 3 to both sides, and I get x is less than 4. Isn't that the answer? Well, technically, yes, this is the answer, but it's not the specific answer. And so as we go forward in math, you're going to find that there are times when we want to be more accurate in our detailing. So yes, x is less than 4, but we can say something more. So I want you to go ahead and write this down, and then I'll pause your film, write this down, and then we'll talk about this. Okay, I'm gonna assume you paused and already wrote this down. So this looks really scary. You see this and people go, oh my gosh, what's going on here? This reads as, this is the set, right? So this is x, and this weird looking E thing, or C with a line through it kind of a thing, is an element of the reals such that x is less than 4. And you put it in set, it's called set builder, so you have to put it in the set. And, oh, that's a horrible, funky chicken. And you put it in the set. So let me break this down. So this is saying x. This is saying element. Element means part of something. So for instance, everybody's heard of H2O, right? Element means, like for instance, water. Everybody knows water. Water is made up of the elements hydrogen and oxygen. 2 hydrogens and 1 oxygen. Those elements make up water. So element just means part of something. So what we're saying here is we're saying x is an element, means it's part of, and this is the symbol for the real. It's called, what'd you call it?
Blackboard art.
Blackboard art, which is like a double R, 2-line R. This is the symbol for real numbers, and we're going to talk about that in a second. So x is an element of the real numbers, and that line means such that. So we're saying x is an element of the reals, and then we do the line such that once in a while you'll see a double dot like that. That also can be such that, depends on the textbook, if you're looking at old textbooks, such that x is less than 4. So I'm saying, in English, all this means is x is any number I can think of as long as that number is less than 4. Why do we need to do that? It's just a more accurate way of talking about numbers. So let me take a step back though first, and let's talk about number groups. So, when you were a little kid, you came home from school and you said, and little Mr. Nelson came home from school and he said, Mom, Dad, I can count. And he goes, 1, 2, 3, 4, 5, 10. Like, oh, Mr. Nelson, you're so smart. Have a cookie. What he was doing is called natural numbers. 1, 2, 3, etc., etc., etc. That's natural numbers. Now, if he had come home and said 1, 2, 3, 4, 5, and his parents said, no, Mr. Nelson, it's 0, 1, 2, 3, 4, 5. Mr. Nelson would have been like, I don't have a 0, because your fingers don't have a 0, right? You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You don't have a 0. In fact, the concept of 0 actually originated in the Middle East. Romans, if you look at Roman numbers, like their counting system, they didn't have a 0. The idea of a 0 is conceptual. I mean, it's the idea of close your eyes and imagine nothing. And you say, what do you see? And people say, I see black. That's something. I see gray. That's something. I see white. That's something. I see fog. That's something. You cannot actually visualize nothing. The actual definition of nothing is the absence of something. So you can think about it, but you can't actually visualize it. So 0 is a conceptual thing. So that's why it's not part of natural numbers. So then Mr. Nelson got a little older. He came home from school and he said, Dad, I learned some numbers. Now, oh, great, sweetie. And he said, what are the numbers? And he goes, 0, 1, 2, 3, etc., etc., etc. And they're like, oh, Mr. Nelson, you're so smart. Here's a cookie. And he was talking about his whole numbers. Now, here's the weird part. You notice that I put whole numbers, the natural numbers, inside the whole numbers. It's because all natural numbers are whole numbers, but not all whole numbers are natural numbers, because whole numbers have a 0. And the way I kind of remember it is that, you see that whole has a hole in it, and the zeros kind of looks like a hole. So I remember whole numbers have a hole, which is the 0. So whole numbers, and then you have natural numbers. Now, Mr. Nelson got a little bit older. He goes, Mother, Father, I have to count for you. And he goes, Mother, Father, 1, 2, 3, 0, 1, 2, 3, 4. And they're like, oh, you've already told that. No, I'm not done, Mama. And he goes, -1, negative. Oh, Mr. Nelson, you're so bright. And what he was doing to his parents is something called integers. Integers. And the way I remember the symbol for integers is a Z, a double Z. And so a lot of times I'll tell my class to remind them that Z is for integers. I'll go zintegers. It's a zinteger because it reminds me about the Z. So whole numbers have a whole, that's a 0. Integers have a Z, so it's zintegers. All right, so now Mr. Nelson got a little bit older and he said, hello, Mother and Father, I would like to count for you. And his parents are like, oh my gosh. And he goes, Mother, Father, I would like to talk to you of rational numbers. And rational numbers still has a 0, 1, 2, 3, etc., etc., etc. And it still has a -1, -2, -3, etc., etc., etc. But it also has like 1/2. It has 0.25. It has 0.3333 going on forever. You can also write it like this. People say, well, doesn't that go on forever? Yes, but it's rational because I can visualize it. If I ask you what's the 10th number back, you know it's going to be a 3. If I say what's the millionth number back, you know it's going to be 3. So it's still rational because I can visualize it. And it also could be 1, 2, 3, 1, 2, 3, 1, 2, 3, going on forever, right? And you say, how is that rational? Well, because I can tell you that the second number will be every time, and then I can tell you, so if I go back divided by 3, I can tell you each number in the sequence. I can go back 100 places, 1,000 places. These are rational numbers. So a rational number means so basically, integers are rational numbers, whole numbers are rational numbers, natural numbers are rational numbers, but are all rational numbers integers? And the answer is no, because rational numbers really are any numbers that can be written as a fraction, right? So not only can whole numbers be written as a fraction, but you can have fractions written as fractions. And then finally, if you have rational numbers, then you must have something called irrational numbers. So you're like, what are irrational numbers? Irrational numbers are numbers, I basically say they're numbers that don't make sense. For instance, the most famous of the irrational numbers is pi. And they're say, why is pi? Well, a lot of people think of pi as 3.14, but actually pi continues to go on and on and on, and it doesn't repeat. And if it doesn't repeat, you cannot predict what it's going to be without calculating. Another thing that you might think of as a irrational number is, for instance, the square root of 2. You say, oh, well, duh, it's 1 times 1. No, 1 times 1 is 1. Oh, what's 2 times 2? Well, 2 times 2 is 4. That doesn't work either. Oh, it's 1 point, put in your calculator. You'll see it goes on forever and ever and ever. It doesn't repeat. It's irrational. So anything that's not something that makes sense, that doesn't repeat, is considered to be irrational. And so you say, okay, irrational, by the way, we use a Q, and I usually do a simple Q, like a double Q line like that. It's for rational numbers, and irrational numbers I do a Q, and this is a Q like not. It's the prime symbol. So it's like Q and not Q. Does that make sense? So rational numbers, not rational numbers. And then, so all those numbers together end up being in a big group that we call the real numbers. And this is probably the most important of the ones we're going to write. So this is the way I usually write it, double R. Real numbers are every number you see here. Pretty much all numbers you can think of are real numbers. And 99% of the time, we're going to use real numbers to describe what we're talking about. But I always say, if there are real numbers, what else can there be? Miss Garcia, what do you think?
Fake numbers.
Fake numbers. What's another word for fake numbers? We're going to call them imaginary numbers. Or, if you know from Eisenhower, we also call them Fongu numbers, because Mr. Fongu is fake and imaginary numbers are fake. So, imaginary numbers are numbers that you have not conceived of. We're not going to talk about that. You're going to learn that in Math Secondary 2. Ho, ho, ho. I'm not going to talk about that. It'll just make it'll make your brain explode. But look it up online. Figure it out for yourself. All right. So, for those of you who kind of got confused by that, let me just show you really quickly, you might want to pause your screen and write down this in your note, especially if you are a distance learner. This is the symbols. I'll write them again to the side the way I usually write them, as real numbers. Natural numbers, I'll do a double N. Whole numbers usually do kind of a weird, kind of a swirly thing. Integers is that double Z. Rational numbers and irrational numbers. Rationals, whoops, I don't know what I just did there. Irrational numbers or rational not. So please write that in your notes, and I'm going to assume you did, so we're going to move on. So now that we know that, how do we put something in set builder notation? Well, here is, let's see if I can make that a little bit bigger. Here is my inequality, right? N is greater than or equal to -3. Again, it seems really hard to set builder notation, but it actually is the easiest thing in the world. All we're going to do is start off with our variable. Whatever our variable is, that goes first, right? N. And then N is an element. Well, let's look at this equation. Or it says N is greater than, or inequality, I should say, N is greater than or equal to -3. So N is any number greater than or equal to -3. So that makes it a rational number. That's going to be 99% of the time you're just going to put R. Such that, and this is the easy part, all I got to do is just put this in there. Such that N is greater than or equal to -3. Funky chickens for my set notations. And so this is read N is any number, or is the element of the real, it's part of the real numbers, as long, such that just means kind of like as long as it fulfills this rule. As long as the number I'm picking is greater than a -3, it'll work. So any number less than -3 won't work. So that's how you do it. Ms. Garcia is going to take you through a couple more of them and keep us going nice and fresh. Good luck.
All right, so we have another one now. So this one, we have the mouse pointing at the G, so we're saying G is less than 12. So we've got to think of, okay, well, what's less than 12? We've got 11, we've got 10. But keep in mind, 11.5 is also smaller than 12. 11.9 is also smaller than 12. So we're going to have to include all of the real numbers. And we know G is our element, or G is an element of our real numbers. And now, like Mr. Craig said, here comes the easy part. Such that we're just going to take this and go ahead and put it right here. G is less than 12. And then, of course, you can't forget, what do you call it, Mr. Craig?
Funky chicken.
The funky chicken.
It's set notation, I know.
Yeah, this is set builder notation specifically.
Builder notation
Set
specifically.
Builder.
But I call them funky chickens because they look like that.
I mean, they do look like funky something. Next up. So this one, we've got a number line this time. And I'm going to zoom in a little bit for, there we go. Yeah, you can. All right, so this one, the one we're going to focus on is this -2. We're going to pick a variable. Let's pick, what letter have we not done yet? H. Let's pick an H. So I have decided H, and now I'm looking at where this number line is pointing us. So it looks like we're going in the positive direction. We're getting bigger and bigger and bigger. So H is going to be greater than, now hold on, is this -2 included? No.
It's not. It's not because it's a circle.
It's an open circle specifically. It's not a filled in circle, which means we can't include it. We don't put the line below it, but we have a -2. All right, we're partway there already. Now we've got our variable H, so I am just gonna actually build off this. Over here, H is an element. Now look at the way this line is. This is a solid line that is covering every single number in between on this number line, which means it's going to be an element of our real numbers. Throw in a such that, cover it in some funky chickens.
Her.
And congratulations, her. Congratulations, we have now built set builder notation. Very nice, her. All right, here's another one. Once again, we've got a number line, so we're starting at 0. Mr. Craig, give me a variable this time.
I'm gonna go with T.
T, all right, so we've got T, and we've got a 0, so we know we're focusing on that 0. We know that the number line is going to the left now, and we know left is less, so we know that T is going to be less than 0, but hold on, is this circle filled in?
It is filled in.
It is filled
totally
in.
Filled in.
And I don't mean the 0, I mean the one that's actually on the number line up here. That is filled in, which means we have to include it. So from here, let's just build set builder notation. Every single number here is included, so we know that T is an element of the reals, such that T is less than or equal to 0. And of course, some funky chickens.
So it's saying T is an element of the reals So long as t is less than 0.
So long as, very true.
Or such that.
Such
Okay.
that, so long, given that is another way you might hear it.
Very
All of these are all true.
Term.
Term. Oh, this is a weird looking one. Okay, so first up we need a variable. So let's pick
F.
F. I like it. Let's pick F. F is the variable we're going to work with here. So this one is a little bit tricky. You got to think, what number are we actually starting at here? Well, it looks like 1 is part of this sequence, but 2 isn't, 3 isn't. So it looks like it's going this way. So we're starting at the 1. Oops. 1. And it looks like it's going to the left in a bunch of dots. So we know this is going to include less than. Does the 1 have a closed circle on it? Yes, it does. So that means it's F is less than or equal to a 1. Now, this is where set builder notation in particular is very useful. Like I said on the other ones, we had that solid line, but this one is no longer a solid line. It's a bunch of dots, which means we are not including the numbers in between our 1 and our 0, nothing in between 0 and -1, nothing in between -1 and -2, and so on. So, this is not actually just an element of the reals. This is an element of a specific set of the reals. Our integers. So we don't include any of the fractions in between, we don't include any of the decimals, it's just the integers, such that F is less than or equal to 1. And funky chicken.
But Ms. Garcia,
Yes,
I
Mr.
have
Craig.
a question. What if I had just put my F and I said, well, it's less than the 2, so how come I couldn't just do that? Because 2 is not included, right? And it's less, so I could put Fez such that. So I'm saying F is an element of the integers such that F is less than 2. Doesn't that work?
Oddly enough, yes, it does, especially because he didn't include this line under our less than symbol, which means 2 is not included. If we're talking about the integers, we would start at 1. This is not wrong. However, in math, we want to be as clear as possible. So while this is correct, this is more precise because this tells us exactly where we start. We don't just hear we don't start at 2. We see that we start at 1.
Okay.
Thank you for that question, Mr. Craig. All right, next video will be for day 2.